Here is an explanation for the answer to final exam question number 86 in Physics Demystified, 2nd edition. If you have the printed book, you'll find it on page 534. This thing here is planet Earth. Couldn't you tell? But this question is asking us about something called the Michelson-Morley experiment. Michelson-Morley. I believe that's pronounced like this. Morley, M-O-R-L-E-Y. The Michelson-Morley experiment was something conducted all the way back in the 1800s, the late 1800s, to determine whether or not the speed of light depended on the direction in which the rays travel through space as they arrive at the Earth from various stars and other celestial objects. Would the speed of light, c, vary or not? Now, of course, the Earth moves through space, or presumably it does. So, you would expect that if the light rays were traveling through some sort of a fixed medium, which they called the luminiferous ether, this was a hypothetical sort of stuff. Luminiferous ether. Well, you know, sound waves travel through air, water, metal. They need a medium in order to travel. It was logical to suppose, or it seemed logical anyway, to suppose that light would also need some sort of physical stuff to travel through, that nothing could travel through a plain vacuum, could it? Well, they wanted to find out whether or not the Earth was moving with respect to this luminiferous ether. It would make sense that it must be. The Earth is not the center of the universe, is it? It isn't absolutely fixed with respect to the entire cosmos, is it? The cosmos doesn't all revolve around the Earth, does it? That idea went out of style with Galileo, and shortly thereafter. It didn't go out of style with the church for a while after Galileo, but it's out of style now, and it was out of style in the late 1800s. So, the deal was, if this Earth was moving with respect to this luminiferous ether, you would think that the speed of light would be different. It would be greater, it would appear greater in the direction that the Earth was actually moving through space. So if the Earth was moving with respect to absolute space, say in this direction, you would expect these speeds to be greater than those. But when Michelson and Morley did this experiment, they found to their consternation that the speed of light was the same exactly, no matter what direction it came from. And Einstein noticed that, and he said it has to be because the speed of light is itself an absolute constant. That way we get rid of all of this gobbledygook, all of this baloney, all of this rationalization. We get rid of it all, and in fact light then can travel through a vacuum. But they still looked for an excuse. Some people still thought that there was this luminiferous ether, and they were looking for any rationalization they could. And they said, well, suppose that the ether is kind of like a fluid, and that in the Earth's atmosphere or near the Earth sort of pulls it along. You know, it sort of pulls a little bit of the ether along with itself as it travels through this stuff. So right near the surface, the ether is in fact fixed with respect to the Earth, so the speed of light would vary as it approached the Earth's surface and would appear to be constant, even though out here in the greater space it might not be constant. For example, then if you were in a little tiny spaceship, not big enough to carry any ether with it, that you would observe different speeds. So they still tried to think up an excuse. So this question, according to some pre-Einstein scientists, the speed of a light ray through space does not depend on the ray's orientation, because the luminiferous ether must travel along with the Earth near the surface, just as the atmosphere does. That was their excuse. In this question, the correct excuse to score a plus on this question is B. Choice B.